And the second one, and the third one, we showed up. Simple question. D, R equal SE. I know, basic. And
Alright, I'm already a little bit late, so I'm wasting time on this drawing. So, class news, double lecture today because Wednesday's the review, so that will be the extra hour. So today, unfortunately, I have to do 2 lectures back to back. It sucks, I know. Anyway, I'll spend a little bit of time in the next hour. We'll do our standard 10-minute break. I promise I won't go over today. I don't think I have a few to talk about in the next hour. I'll tell you a little bit about the test in the next hour, and then we have to get back to, we gotta get back to this stuff. Sorry. I'll help you a little bit on homework. I'm sorry I was late about that. It's that the present homework is all about adiabatic changes. That's actually, it's not the whole homework, but it's most of it. And adiabatic changes are very difficult because I have to give you kind of starting and stopping points. The problem is if I screw those numbers up, the question is unsolvable. So I have to double check it, triple check it. I triple checked it, had my graduate student checked it. And anyway, it just took time. So sorry about that. Anyway, your homework is up. Don't ignore it. It's definitely one of the longest ones you've had. Lots. Calculator, 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 calculator. So I am writing your test. There are going to be calculator questions. There are going to be adiabatic changes. This homework will be on the test. So go ahead and start on it. Don't. Like a lot of you are doing this on Wednesday. I know that because it's on my office hours and you haven't started yet. I would rather you not do that, but if that is your situation, you probably should come by office hours. I'm not going to hold it against you. I don't even know all your names. I'm just kidding. So, okay, anyway, so I am writing your test right now. I'll have it written by Monday. Wednesday we'll review. And that's good because I know it's on the test and you know that I bleed answers. You just poke me just slightly. Not like a chainsaw, don't do that, but just pry me a little bit. You know I'll start spewing out answers. It's better if I know what the answers are ahead of time. So again, Wednesday review. So I'm not sure what else to say, other than I made a giant mistake last time, and I was supposed to write a handout about that, and I didn't because I've been too busy with all the crap that they keep throwing at me. I have reviews, I have grad students, I run a lab, I have to make money, and I'm going to buy some kitties. I'm thinking about buying heroin and bath salts too. Oh, you know, my cat, she'll be like a hero, but she's a she, she's a hero witch. And bath salts was more relaxing than bath salts. So, everyone's been looking at me when I tell them I'm buying heroin with bath salts. I don't know why. Anyway, so, okay, let's do the change of, okay, so let me just review what we did before. We talked about the, this is glass wool, by the way, when I draw it like this is glass wool. Last time, before we get into my mistake, last time we talked about Joule and Joule Thomson experiments, and the Joule experiment, which I kind of spent a lot of time on. Remember, it was just, they started figuring out about, they started figuring out that this stuff was real. I mean, remember, at this time, they still didn't even know air existed. I'm not kidding you. They thought that when they were doing all these experiments and figuring out that the Kelvin scale, they didn't even know that they were measuring the temperature of air. They thought it was something they called ether. They knew that something was there, but they didn't know what, and so they called it the ether. So you can even look back, because the journals now have published everything they've ever published, and so you can look at Journal of American Chemical Society from 1880, that's when they started publishing it, and you can see research on the ether. And there's actually this one article I read in the Journal of American Chemical Society from like their second issue about this guy who tortured dogs for days, and he wrote about it. It was horrible. Anyway, we moved on. No more dog torture. I already forgot what I was talking about. So anyway, so they were just testing whether their general ideas, these equations that they had, they were just testing whether they worked. So Joule built this really strange machine. Here, I'm just going to write off the cuff. So don't write this down. I just want to remind you, because I'm speaking off the cuff. Joule was just wondering whether any of this worked or not, without even knowing what he was doing, and wanted to measure the change in temperature with respect to volume at constant U, and that ended up being minus 1 over CD, change in U with respect to D at constant T, which of course is a small number, as it should be because of that, and didn't get an answer, but he didn't really expect one, so he knew he was kind of on to the right thing. And again, this not only measures, does any of this actually work? He found that, again, it was a very small number, but he already knew that the change in U with respect to T should be 0 to small, and that's exactly what he got, so he felt pretty comfortable about it. But then he went to the soon-to-be Lord Kelvin, Thomson, and with Thomson they invented a new device. Now I'm drawing it a little bit better than I did the other day. So you got remember the zeolite thing, the thing that's a plug with a lot of little holes in it? You engineers, I'm certain you know what zeolites are because it's the most common type of substrate for catalysts. So basically what you chemists, engineers, this is what their lives are going to be. Sorry, I already know that. Maybe you'll get hit by a bus and you won't have to go through this. But in the petroleum industry, they take zeolites and then they embed metal particles on them, metal nanoparticles. And those are catalysts for all organic transformations. And so, because they're full of little holes, they carry a lot of volume for a small amount of weight. That's why they're good catalyst substrates. So that's what they did. They got the zeolite, put it in the cylinder, wrapped the cylinder in glass wool, and as I didn't really do a good job of this last time, they pushed on one side and pulled on the other. Eventually, the plunger came to an end, and this one was pulled out as far as it went. And sorry, I shouldn't have done this. Change in work. Sorry, I'm being idiot. Change in U1. All right, it's 80 basic, so that's the change in work, and then, yes, I'm trying to be more careful with my notation. I'm not going to do the integrals because it's rather pathetically easy. This was P1, B1. This was minus P2, B2. Let's see, compressions are positive, expansions are negative. So that totally makes sense because these have to be positive. So anyway, this is what they did. Now, what I screwed up last time is I did, what did I do? I did the change in U. I corrected it. So I made a terrible mistake last time. I talked about how U2 minus U1 ended up giving me something that was wrong. So what I did last time was wrong. So where you see this, I'll write this down, but don't write it down. Cross it out. What I did was, I said U2 minus U1. If you see that, cross it out. That was wrong. I did it wrong. You see, I wasn't calculating U1 on U2. I would do that with the equivalent theorem. That's the only way to do it. I did not calculate the absolute value of U1 and U2 and subtract them as a delta U. It could be done that way, it could, but that's not what I did. I calculated the change in U2, and I calculated the change in U1. And therefore, the total change is the sum. That's what I screwed up. And a lot of you caught me on it, thank God. 8th time I've taught this class, first class that caught me. That's actually kind of amazing. And I feel really stupid. So the change in U1 and U2 was the change in P1. Well, so this is really the net change, right? So net work 1 plus, net work 1 plus the change in work 2. And therefore, what you found was that the change in U2 plus the change in work, which is P2, V2, is equal to the change in U1 plus P1, V1. And these are also changes because you wiped it out, right? The ending U is 0 because there's no mass. There's nothing in there. So this is technically the change in P2, V2, and the change in P1, V1. Just not a question.
Shouldn't delta U1 be negative? Just wondering, since we're sending it to the other side.
No, because I've worked them correctly. I'm kind of skipping some steps here. So, right, so this is P1, V1 minus P2, V2, so I brought the P2, V2 over here. You see that? Right, negative, positive.
Yes.
Right.
Yeah.
Let me write it down. P1, V1, see positive, positive, minus P2, V2, but then I brought that over here.
And U1 you sent it over there, right?
And how did I do that? What have I done? I made another mistake, haven't I? When did I do that? I made another mistake, and I'm not sure how I did it. Sorry about that. Okay, I just definitely need to write you guys a handout. What did I do? What did I do? You're right, because I changed one, but I didn't change the other.
It should be just negative delta U1.
I know, but I've done it wrong, that's why. Jesus Christ, I can't believe I had taught this 8 times and I'm still screwing this up. Jesus Christ is wrong in my notes, you're right. Sorry folks, again, let me sort this out and I will send you a handout. I am definitely screwing this up. Sorry about that, I can't, sorry, slight panic attack right now. During the break, I'll go, I know it's in my book, it's been years since I looked at the book because I've been doing this too much. And that's really the problem, and you're right, there should be a minus sign, and that means that this should not add up, but it does. But anyway, H1 is equal to H2 is equal to H1, and I'm missing a minus sign, and I don't know where, but I guarantee you this is correct because it's in every freaking textbook that's ever written, and you think a freaking PhD who taught this 8 times would know, but he doesn't. So, sorry about that. Again, I hate it when I do this every now and then. Look, I'm going to screw up and I'm not going to figure it out, so I'm just going to move on and hope you just accept that this is the case, and then I will figure it out and fix it later. I know better than to sit here for 10 minutes. Have you ever had that, like a teacher screw up and get confused, and they sit there for 10 minutes until they figure it out? That sucks. I'm not going to do it because that sucks. Anyway, had that happen to me a couple of times. I will fix this anyway. H1 is H2. I promise you this, if this is correct. I just always have some problems with minus signs. So anyway, sorry. Anyway, the problem comes down to, remember that they're simply testing thermodynamics, and what we were trying to get was the change in temperature with respect to pressure, and I will eventually prove MOP was held constant. Yeah, I'm sorry, I'm horribly embarrassed. So going to delete that. You know what I'm going to do? I'm going to come back and refill myself and get it right. I'm not. I did that once, all right? So anyway, so this is what we're ultimately trying to get to. And this is, of course, as I mentioned before, it's the Joule-Thomson coefficient. Don't ever try to remember that. It doesn't matter. But it may be on your GREs and whatnot. I just don't know. And again, I need to expand. I'm going to pick an energy function. Obviously, I'm going to pick H. and I'm going to write a change in H as a function of a change in, well, I guess I'm going to go with temperature and pressure. Is that what I guess? That's what I did. And then I'm going to do some steps to draw this out. I'm going to put it on the left. Hopefully I won't miss any minus signs. And then I'll understand what makes this what it is. Now again, same situation. If T is constant, H is 0 for perfect gases, you're actually going to do on the next homework after the test, you're going to actually do this for real gases with van der Waals. And you're going to find that the change in, if T is constant, H is not necessarily 0. It's small, but it's not necessarily 0 for real gases. For perfect gases, if T is constant, H is constant. You're going to do one of these calculations, you got a derivation to prove that. You may even have it on the test. So anyway, again, as usual, I'm going to start with this. And get used to this next. The week after the exam, we're going to spend an entire week doing nothing but this stuff. And I'm going to expand it. And again, I happen to know that I happen to want to choose T and P. So if I'm going to change T, I better hold P constant. Now again, one of the few rules is now that I've decided that I'm looking at H as a function of T, but I held P constant, then I'm obliged to do this, then I hold the other variable constant, and there we go. Okay, never seen minus signs, what a miracle. All right, now what I want to do is, let's see. Okay, this one, wait a minute. Yeah, okay, this one, what is that? You already know this one. What again? Okay, all right, I'm changing temperature. I'm changing temperature. CP, right? It's heat capacity at constant pressure. Right. Now we've done that. So anyway, pressure constant. How much energy changes with temperature at constant pressure? Now normally this is heat over temperature at constant pressure, but heat is enthalpy, not internal energy at constant pressure. So the dq dt becomes dH dt at constant P, and that's Cp. Okay, you know that. I'll rewrite this part. dP. Okay, and change in H. Now I set you. All right, we're on the test. I've set you up with this because I'm not that cruel, and I've asked you what this is. Now, okay, I got to draw this out, but I can see that my only way is right there. So I'm going to divide by the change in pressure. There we go. That's the thing I'm looking for. But I see that I have to hold enthalpy constant. Oops, sorry. I have to hold enthalpy constant. There we go. Not that it matters. When you're in these situations, it doesn't matter. I'm not even going to ask. It's 1. And there we go. So I can see that if I take minus the change in yeah, I actually recognize your voice, by the way. Okay, if I do this, I get my Joule-Thomson coefficient. I'm still hearing you anyway. Okay, so sorry, not my best handwriting day, but well, there you go. So how enthalpy changes with pressure. And again, this is going to be a measure of the imperfection of gases. So they get small numbers. Joule and Thomson do, they get small numbers. But this machine actually works a little bit better than Joule's machine. And by the way, there's a reason for that. Joule-Thomson coefficients, sorry, I should write this. Again, not that I care. Joule-Thomson coefficients are larger than Joule coefficients. It just works better. It's just a practical thing. I mean, you found on your homework, yes, I hear you. You found on your homeworks that enthalpy is always greater than U because of that plus PV term. It almost always takes it more negative or more positive. It's always a bigger number. And so that meant that this machine simply worked better. So when Joule and Thomson did this experiment, they actually started getting values. Small values as they expected, but they knew that you get something because gases aren't perfect. And again, the imperfection comes here. Perfect gas is 0, but when you have perfect gases, this is not 0. And again, you're going to do that on a homework. You're going to do this. You're going to do this calculation. You're going to do this guy right here on the next homework. Really, come on. Just knock that off, really. You're really trying to crazy right now. So you're going to do this on a homework for perfect gases, and you're going to find it 0, and then you're going to do it for van der Waals, and you're going to find it's not quite 0, but it is a very small number. So Yeah, what else do I want to say about this? Let's see, what makes it negative? Let's think about this. Now, funny thing about pressure and volume, they always work opposite of each other, right? If you expand something, the pressure goes down. So let's say that this is negative. All right, let's do that. Yeah, and now again, very likely a question, very likely a test type question if it's negative. Let's see that. If this is negative, then this has to be negative. This has to, come on, I'm not going to ask again. Shut up, really, shut up. I'm getting sick of this. All right, I don't mean to yell, but I swear to God, you guys are all running your damn mouth right here. All right, this is negative, this is negative. That makes all this positive. All right, this is automatically positive, that makes pH2P positive. That means if pressure goes up, enthalpy goes up. And that's, what would that be? That would be a bad thing. That would be, let's see, let's draw that. And I'm just doing this off the cuff, by the way. Okay, if this is negative, then this is negative, but then the remainder is positive. This is automatically positive, that means this is positive. That's a positive slope. It's a positive slope, that means like this. Okay. JT is negative, okay? And that means the opposite is true. Yep, if you're positive. Okay, there we go. All right, so I can see that this is kind of the opposite. I've never actually done this before, so I'm sorry, I'm a little wonky right now. This is pretty much the exact opposite of what I did yesterday at the U as a function of volume, because if I pressurize something, things get closer together. Now, this is definitely molecules like each other. Energy going down is always good, right? Energy going down is always good. And so molecules are liking each other. Their dipoles are lining up just the right way. These things don't like each other. They're hitting each other. They don't like to be in the same room. They're siblings that are competitive. And so you gain energy, which is bad, right? That's always bad. So anyway, now that we understand that, and I might ask that on the test, I'm thinking about it, think about your test all the time. Let me give you some numbers. And, by the way, so let's, units, okay, temperature versus pressure. Well, we can do this. Let's see. Enthalpy is joules. CP is joules per K. So that was K, joules over joules. That's K over pressure. Okay. So this has to be in units of K per atmosphere. And then let's talk about what gas. Okay, I guess I wrote this reverse. Minus 0.03 is H2, is helium, which is a little bit worse. Minus 0.062 air. Air Jordans, those are 0.182. Ammonia, which is very topical, I'm going to talk about this in a second, 0.95. Now, again, remember, these are kind of small. These are definitely kind of small. And then Freon. Freon is a chlorofluorocarbon. It's a bigger number still. Okay, now, what's important about this is that, okay, the positive guys. If I depressurize something, then I'm sucking away heat. Okay, I just gave the answer, right? If I depressurize something, so I'm going this way, enthalpy is going to take something. It's going to get fed, but what feeds it? Heat. Ergo gets cold, right? Now, and I think you're well aware, these things will get cold. Now, these guys are, again, remember, these are oddballs. These are oddballs in a weird machine. So if I pressurize them, they get hot. And they're angry. They get hot because they're angry. Because they don't like being together. So, but no, sorry, wait a minute. No, if I pressurize these, no, sorry, my bad. What did I just say? If I pressurize them, they get cold. If I pressurize these, they get hot. If I depressurize them, they get cold. If I depressurize these, they get hot. And again, it's because these guys don't like each other. They're very different. And these guys don't want to be together, these guys do. So, sorry, got that screwed up. Now, you may notice that this is, it shows Freon for a good reason. You're seeing why refrigerators work. It's their Joule-Thomson coefficients. It's how a refrigerator operates, it's how your freezer operates. It pressurizes a gas, it used to use Freon. It generates a lot of heat. Now, when you hear the fan kick in your refrigerator, that's why. It went through a compression cycle. It went through a compression cycle, and then the compressor got hot. It got so hot that the machine will break if it doesn't cool itself. It just uses a fan, it's enough. Doesn't need to do anything too fancy. There are fancy ways to do that. But the compressor got hot. You can't let the compressor stay hot or it will break. So the fan kicks in and blows the heat out. And now that the compressed Freon then goes to the freezer compartment down these series of tubes where it depressurizes. Why? Because the volume increased and it got cold. So that's exactly how modern refrigeration works. And maybe I'll ask some questions about refrigeration coming up. Maybe next week. I normally don't, but whatever. Okay, here's a cool thing. All right, Freon was a relatively modern invention. Those are chlorofluorocarbons. Can we still use them?
Not really.
No, of course not. No, not really. They're illegal. So I guess ISIS still use them. That's how bad they are. They are bad. No, Freon, actually what happened with Freon was people figured out it destroys the ozone layer. That not only does it destroy the ozone layer, for you engineers especially, it's a catalyst. It's a catalyst that keeps destroying the ozone layer. That's the worst situation possible, right? So the entire world banned them. And I'm actually not sure, but there maybe some engineers know what they replaced it with, because I'm not sure. Okay, but anyway, so Freon is again a relatively modern invention. Ammonia, you know what they discovered ammonia in? This is disgusting, I shouldn't say it. Horse piss. Horse piss has been around for a long time. People have had oh, I have a cup of it right here. No, all right, so ammonia has been around for a long time. So back in the 1800s, all right, really up until around the 1860s or 1870s, they would cut ice out of Lake Erie, and there was a bunch of trains went to Lake Erie, and they would go down to like where I grew up in Mobile, Alabama, and ice trucks would come by, and you put it in your ice chest, and that was your refrigerator. Literally, the ice came from Lake Erie. In fact, one of my family members, I make a good income, but I'm not exactly rich. One of my family members is rich because his father, he's pretty old, his father was the treasurer of the EM&O Railroad. No, it's not Monopoly. All right, but if you're ever driving around upstate New York and you see train bridges, you'll see EM&O still written on them in fading letters. Erie, Mobile, Ohio, and Mobile is where I grew up. And that was the railroad that carried ice all over the southern United States. And then they went under, now all the railroads are CSX or whatever they are. Okay, so anyway, that's how they did it, and then somebody figured out how to make a refrigerator. This was the best choice. This didn't exist, and it was a good idea. This sucks. This is like, 5 times better. So they made refrigeration plants out of ammonia. I think I told you the story already, but it bears repeating. It worked. So places down south could then generate their own ammonia using refrigeration by compressing ammonia and then expanding it. Got super damn cold enough to freeze water. Problem. Any of you remember the story I told you? What the problem is? It tends to explode, like really freaking easy. So, compressed ammonia is impossibly dangerous. It's one of the most dangerous gases you could ever handle. And these things would explode. And when they did, ammonia shot everywhere, and you could lose an entire town. And that actually happened way back when, in great-great-grandparents' day. In fact, one of the best movies I ever saw is La Mesquite Coast. Harrison Ford's biggest movie after Indiana Jones. I'm sure you can download it illegally. I guess that's the ending of the video. It's a pretty old movie. I mean, most of you probably weren't even born when Raiders of the Lost Ark came out. I was only about 6 or 7. So, anyway, it's about a guy who lives in just some rural area and he gets sick of it. And he decides to, move away from it all and get away from technology. So he moves to Nicaragua or somewhere in the rainforest. And what he does is he tries to help the indigenous people live better lives. So he builds things, and they're like, oh, that's nice, it's really comfortable. And then he gets sick of not having ice, so he builds an ammonia refrigerator plant and subsequently kills everybody at the end. I guess there's no reason to watch it because it just told you the end. But anyway, it is a good movie. So, all right, now I want to think about what's responsible for this effect. Not that you're not going to calculate it at some point. Deride it. I know that this is obviously a source of imperfection of gases because it ought to be 0 for that. And I know that C's ought to be 1, which is a question on your exam, by the way, so just get it. And I know that, did you hear that? Anyway, I know that hydrogen, helium do like this, but CO2 does like that.
Now, I know that CO2 is different from helium in that its attractive forces dominate. As in most gases, attractive forces tend to dominate. And then this is zero. Right? CO2 drops a lot, helium rises, and this is like 100 atmospheres. Your refrigerator does not operate at 100 atmospheres. That's shockingly dangerous. Just a couple atmospheres. So, what was that thing? Anyway, so if I see that molecules like CO2 and Freon and ammonia have definitely very strong Z factors, and they do, that's intermolecular forces. So why does my refrigerator work? What do I use as a refrigerant? I choose something with strong intermolecular forces. So strong intermolecular forces are what make this positive and make your refrigerators work. So anyway, that's kind of obvious. All right. Sorry to be so bitchy today. All right, so again, let's summarize Joule Thomson. Gases aren't perfect. I hold temperature constant. The energy shouldn't change, but well, actually they might. If you mess with them the right way. If you increase their pressure, if you decrease their volume, whatever. They shouldn't change because you hold temperature constant, but they do. Remember that these exist outside of our comfort zone. Remember that we do things. Let me back up a little bit. When it comes to the test, because that's probably what you care about most, I'm going to say, a gas expands isothermally and reversibly. A gas expands adiabatically and irreversibly. I'm going to be like that, all right? And then the equations are on the cheat sheet. You solve them, everything's fine. And then I'm going to ask you, what does it mean to be adiabatic? And you say, well, it means that the thing is wrapped in glass wool. Okay, you've got 100% on the test now. Now remember, Joule and Joule Thomson, these guys are outside of that comfort zone. And that's fine. I mean, the comfort zone, either you're keeping temperature constant or you're not heating anything, because heat and temperature are kind of, they're flip sides of the same coin. So either keep one constant or the other constant, and those are extrema. Extrema of how a machine can work. The Joule and Joule Thomson are kind of outside of that zone, because instead of keeping temperature or heat constant, instead I kept H constant or I kept U constant. Different types of machines. Not machines that we care so much about. It was nice that they did all this and showed us how all this stuff works. It showed that we were on the right track and people kept going. And you're going to do some derivations. You're going to drive that sucker there, and you're going to figure out how it works. But when it comes to the test, I'm really going to stick with the comfort zone. I'm going to say isothermal reversible. I'm going to say adiabatic reversible. All right, and then you're going to work it, and you calculate it out and fine. All right. So anyway, that's the big picture on these guys. And I'm going to drop it now. What we're going to do now is we're going to start to expand into those last variables. And I'll tell you on Monday where I'm going to cut off the test because I'll have written it by then. I'm tempted to put 1 or 2 questions out of like 15, so that means nothing, based on what I'm doing now and based on what I'll do Monday. But I'll let you know. All right. Besides, when I review, I'm going to spill my guts like a fish. Trust me, I'll make it up. So we're going to get into those last variables. That was entropy and Helmholtz energy and Gibbs energy. Those are the last 3 that we have to cover. Unfortunately, entropy is divided into 3. Entropy of the system, the surroundings, and the total, which is the sum of the 2. So I guess it's really 2. So we have 4 more thermodynamic variables to cover. Unfortunately, we're going to start with entropy. Unfortunately, entropy is very freaking hard. Entropy is the hardest thermodynamic variable to understand. And I spent this is what I have a PhD in, by the way. I mean, you can read my thesis, it's online, it's at UC Berkeley's website. But I can tell you that, entropy I found to be a very difficult thing. My thesis isn't about entropy, but I spent almost all my time in graduate school doing things to understand entropy, although it never really appeared in my thesis. So fortunately, hopefully I can explain this well. Sometimes when you know something too well, then you can't explain it at all. But so we're going to cover entropy, and then entropy is a gateway to the other 2 energies, Helmholtz and Gibbs energy. Now the first thing we're going to do is inexactness of Q. I guess I have to express that as a change. Right? There is no Q, there's only change. There's no heat, there's only changes of heat. There's only heat exchange, there is no heat. That's weird, but it's true. Okay. Now, I've shown you that inexactness, don't forget this, I swear to God. Oh, yeah, I just wrote a question. I wrote a test question in my head, so write this down. Inexact means that it's whatever it is depends on how you did it. It's path dependent. Now, I said work and heat are path dependent, and that's kind of about it. Because the sum of the two is not path dependent, which I still can't really grasp. I'm trying to figure it out. But anyway, so I showed you that work isn't exact, and I did that with graphs, right? Reversible versus irreversible. Those are paths, and it's path dependent. The answer changes depending on the extrema of what you do. Do you do it this extreme way, reversible, or do you just go this other way, this extreme way, irreversible? One or the other. Which one do you choose? All right, so in those graphs, I showed you that the change in work depended on how you did it. Heat is the same way. It's just a lot harder to see. And so I'm going to prove that. Now this is going to be, I am not putting this on the test, okay? This is going to be pure pain for the next 20 minutes. And when we're done, you can bitch about me, and then we'll come back and then keep going. So I'm going to prove that heat is inexact. That heat is path dependent. But I can't paint a picture, I can't heat a cup of water and show you that. I'm going to have to derive it. I'm going to have to use that Clausius inequality. Now, hopefully some of you remember that I said, back in the day, I said that the Clausius inequality, I went over the Clausius inequality for inexactness or exactness, whichever. And I said to you, it's coming back one day. Well, that's today. And we're going to do it a couple more times. All right, we're going to start here. And now, of course, I want to isolate heat. So that's not hard. Changing, changing U minus changing work. So flip twice there. Sorry about that. Hopefully I haven't screwed up a minus sign. Now what I want to do is then, as in all things, let's see, change in heat is, what do I want to do? Sorry, I'm screwing up, my bad. I should have used a different view on that, my fault. Let's see, I want to do the, sorry. Okay. Sorry, I did not review this. Let's get to this guy first. All right, so this is a bit of an aside. This is my derivation outside the derivation, and I'm going to expand this as a function of temperature and volume. Because I know that temperature changes you, and I know that doing work, which means the change in volume changes you. And so this is the change in U with respect to volume, constant temperature. And of course I've got a temperature constant, so I'm like to do this. And let's see. Now, what I'm going to do is I'm going to be uber friendly right now. Wasn't before. I'm going to be uber friendly right now, but I can eliminate one of these terms if I'm a perfect gas. And remember, that's me being friendly. One of these terms can go away. Thumbs up, thumbs down. It's thumbs up. So, why? Why thumbs down? Why? Temperature's constant. Let's make it 0. That's perfect gas. Okay, just so your notes, when you're reading your notes, you don't, like, wait a minute, why did I have? Okay, so let's do the change in heat is change in U with respect to T, constant V, dt, plus, for work, I'm going to do this reversibly just because I can. So I'm going to use dP dV. Again, this is reversible work. I just decided I'm going to do it reversibly. Because why not? Remember, when I'm talking about changes in U, when I'm talking about changes in U, I can do it any which way I want, so that applies here. That's ultimately why, so I won't get into it any further. And what I want to point out now that this looks, two things. For one, just I want you to, instincts kick in. What's that? Come on, you know what it is. CV, that's right. I won't call it CV for a certain reason, because I want to remind you of this. The x a constant y, change in x plus f, and y, constant x and y. Okay, again, this is our Bible. This is the number one thing that will get you through this class. Now, it's clear to me what's what. This and this. Okay, there. do that. Okay, so F is Q. Of course, it's only a change. X is T, and Y is B. So there you go. Now, what am I going to do with this? Again, this is unfortunately has to be abstract. I have no option. This must be expressed abstractly. And the most abstract thing I think you could ever do is to tell you that the change in F with respect to X and constant Y is equal to the double derivative of the same if I permute the derivatives. X constant Y. Right, that's the Euler formula. So I'm going to prove that heat is inexact by showing failure of this. I hope you can live with that, all right, because that's really all I got. Okay, so now that I've got my S and X's and Y's, let's write it down. Make certain I know what I'm doing. Let's do this guy. What do I want to do? I want to do this one. Do I want to do this one first? What am I doing? Sorry, I'm going blind here. X's. Sorry, I'm going to do this one. I'll do this one first. Okay, so change of volume, Y is B, of Q, change in Q with respect to temperature, constant volume, constant temperature. Right. Again, that weird notation, but it's not. Okay. Now, okay, dq dt at constant V, dq dt at constant V, where am I at? dq dt at constant V is the, sorry, I'm going blind. It's got to be this, right? Right. At constant V, this is heat. Yeah, what am I doing? I'm sorry, I'm just going crazy there. U at constant volume is the same as heat, right? One of those lies we told you was fraction. Okay, so this is the change with respect to volume of the change of heat, change of heat, which is U, constant V, constant T. Okay, now this is a cheap shot, but what else have I got? I know that U is exact, and that means I'm going to invoke the Euler formula to prove that it's wrong. That sucks, this is what I'm going to do. So, U is exact. Now remember, this is the Euler, all right, I'm going to do this with U. Therefore, the T, hopefully you can see what I've done. All right, now I'll do this bit again. Don't write this down, but I just wanted, just so you're not blind what I just did. This is a bit painful, that's why I don't really have this on tests. Anyway, I just permuted this because U is exact. I did this, right? I hope that's clear. Okay, now again, I told you from the very beginning, I'm being friendly. What is this? Just for your notes, there you go. Zero. Units? Oh hell, I don't know what the units are, screw it. Don't even do that on the test because that's about half your test. Anyway, it's a third of your test. So anyway, so that's 0. All right, now I got to do the other side. And I better find a 0. And if I don't find a 0, and I'm not going to find a 0. And that's a problem. Okay, so I'll write all this down again. Sorry, let's get this. And then we'll break for 10 minutes. All right, let's see. Now I'm going to do the other side, which is the U dt, the U dV, V, that would be a constant T, and, okay, F is Q, a constant V, that's U, Y is V, a constant X is T, and what is that? That's P. Okay, so this ends up being dP. I can see that. This is this, which is this. P. So don't get that lost. I bet that's going to be a hard part for your notes. I'm really doing this. I've evaluated this. This is all P. Okay, what's that? Well, this is pretty easy. Again, I've already invoked perfect gases, so I have to stick with it. nRT over V, constant V. Again, one of the times that the constant doesn't really matter. nR over V. And let me make sure that I actually did that correctly. And the question is that equal to 0? No. So heat is inexact. There you go. All right. So what I'm going to do next time, in the next hour, because unfortunately we have to double lecture, is we'll take so we're going to break early, but then I'm going to start early, right? Just 10 minutes. 10 minutes, because I'm actually, by the way, just FYI, I'm 1 day behind on the calendar. I'm not freaked out about that. I'm not going to speed up by a factor of 2 in a day. I wouldn't do that to you. We're just going to go slow. It's fine. What I want to show you next time, in the next hour, after we take our break and the camera recharges, what happens if I do something very trivial? And I simply divide heat by temperature. Is that exact? And if it's exact, it's path independent. It makes it a state variable. It makes it important. What is it? Come on, you engineers, you already know what it is. Yeah, it's a technical thing. Oh, God. Anyway. All right, sorry to be so bitchy today, but I'm bad. So, 10-minute break. Smoke them if you got them. Camera recharge. Don't let anyone...